Okay, we are back. Let's get back into things, but any questions about what an enumerator is? So we can actually show an example of an enumerator. For instance, for one in sigma star, if it's empty string 0, 1, 0, 0, 0, 1, etc., then I can enumerate that language. There's one way I could enumerate it is putting #, then empty string, #0, #1, #0, 0, 0, #0, 1, #1, 0, and just keep spewing out all strings in sigma star. Yeah. Because of the empty string. Yeah, there has to be a non-empty character in the cell. It's representing the empty string. Yeah. But I could, for instance, do the same strategy I did above where I do the first string once, then the second string twice, third string 3 times, fourth string 4 times, fifth string, and then keep going. As long as I can guarantee fixing a string, it will be printed. Yeah.
How are enumerators useful?
It's just another way of thinking about computation. So instead of like feeding a bunch of strings to see whether they're in the language, I can just ask the enumerator for another string and it'll be printed, and then I'll know, oh, that's in the language too.
So
Yeah.
it's a way to pick out and then
Yeah. Yeah, instead of having to maybe wait a really long time for the computation to finish, then I can just ask one time and it'll just print the string right there. Yeah. Other questions? So if I want to show that recognizable and enumerable languages are the same, the easiest way to show that is if I can convert a recognizer into an enumerator with the same language, and the other way around, an enumerator to a recognizer. And the easier direction is converting an enumerator to a recognizer. So I have this thing that if you ask it, will print out another string nicely. And now what I want to do is build a machine using this enumerator to be able to recognize the same language. Okay? So here, an enumerator has no input that's given, and it just spews out strings, whereas a recognizer is given a string, and we need to say accept or reject based on what it does. But here's the key. For a recognizer, do I have to say reject? No. But in that case, could I run forever if the correct answer is reject? Yeah, I could run forever. So we're going to actually use that here. So what we're going to start doing from here on out is a high-level implementation or syntax for describing Turing machines. So instead of telling you the input's on this tape and it looks like this and the transitions look like this, I'm just going to tell you if you're given input X or some string W maybe, step 1 is this, step 2 is this, step 3 is this. And so that's a high-level description of what a Turing machine can do. So the syntax for this is, with open quotes, on input W. So that's telling me if this, so I'm building a recognizer here. If I'm given the input W, now I want to say accept or maybe reject based on what the steps are going to do next. And our goal here is to have the same language as what the enumerator did. Okay? So let's see. If W really is in the language, what do I know about that string and the enumerator? If it really is in the language. It'll be enumerated at some point. What if it isn't in the language? It will not be printed, ever. Is that a problem? No, because I don't have to halt on strings not in the language. So what is a good strategy? Just keep asking the enumerator for new strings. If any time the string outputted is equal to my input, what should I say? Accept. So that's the strategy. So keep asking so this is very low level. Keep asking the enumerator for another string x. So I asked the enumerator one more time to print one more string out on the tape, and then now we need to just check if that was the string that I was given as input. Yeah.
Okay, the thing I'm getting hung up on though is like, isn't like 2.7 million years a finite amount of time? So
Yep.
couldn't it take 2.7
Yep.
million years and we never know?
It can take a Graham's number to the Googleplex number of years.
So how?
Number of lifetimes of the universe.
Okay, so how are we supposed to know whether or not it is actually finite?
But what is finite?
Because it goes one to the next.
I don't know what is finite.
Sorry, but how do we know that it's a finite amount of time that we accept an input W?
I don't.
So we're just, this is just, you said high level, so we're just like
I-
thinking about it.
But I know that asking for another string takes a finite amount of time, always.
Yeah.
So if it is in the language, it will be printed sometime. I'm guaranteed that by the definition of enumerator. If it isn't in the language, it'll never be printed. And so this machine will run forever. But that's okay because it's a recognizer.
I just don't understand how we would know if it's like running forever versus just not there yet.
Yeah, so that's,
Or does it not matter?
it won't matter here.
Okay.
So if W is equal to X, we accept. Otherwise, ask for another string. And that's the whole recognizer as a high-level machine. So let's just make sure that this idea works. If W that's given to me as input really is in the language of the enumerator will print it eventually in a finite amount of time. Well, we just keep asking for another string, and so therefore sometime the enumerator will print it. And then I just check if it's equal, and I'll accept.
It's like the equivalent of monkeys in Shakespeare.
Yeah, it actually is exactly the same idea.
Like if you take 1,000 monkeys, put it in the room, eventually one will print.
Yep, it's the same thing here. But, so we are really talking about monkeys and Shakespeare here. So, but now let's just check if W happens to not be in the language of the enumerator. If it isn't, will the enumerator ever print that string? No. So therefore, it'll run forever, but the recognizer does not have to halt on strings not in the language. So it's okay it runs forever. I can't claim that this is a decider because it actually isn't a decider, but it certainly is a recognizer for the same language as the enumerator. Okay? Yeah.
Maybe I'm just not getting it. All an enumerator does is give you strings from the language.
Yep, that's it.
Like a language can be
Correct. Pick your favorite string. It will be printed in a finite amount of time.
that's just based on like how it works.
Yep.
We're not actually proving that.
No, that's the definition of it. Okay. There are infinitely many strings. So an enumerator, if you just set the enumerator by itself running, it will run forever. Always. Even if it has finite language, it'll always run forever. Because even if it has finite language, it'll just print the same strings infinitely many times. But I'm guaranteed for every string, it will be printed in a finite amount of time. I didn't say that all strings are printed in a finite amount of time. I've said every single string will be printed in a finite amount of time.
Is there any connection between countability and
Yes. Because you can only print, it's somewhat related. It's not, it's kind of hidden, but what you can do is show that the set of every language, like all languages, that forms an uncountable set. And the set of all Turing machines, that's a countable set. So therefore, a vanishingly small fraction of all languages are decidable or recognizable. So because the way that you can show that is you can imagine that that a language is just an element of the power set of sigma star. Because it's just a subset of sigma star. Well, the set of all subsets of sigma star, a countable set, is an uncountable set. But a Turing machine, you can think of as, let's say, a computer program. That is a very long binary string. And any two binary strings, any two programs do not correspond to the same integer. So therefore, there's at most the number of integers, number of programs. And so therefore, they only form a countable set. And so therefore, you can't recognize all languages. But that doesn't tell you what languages are not recognizable or whatever, but we'll show that eventually. Yeah. So there is somewhat of a connection between countability here.
Is that proof somewhere that you can
Yeah. I don't think the proof is explicitly stated, but the proof of the natural numbers being a strict subset of the real numbers, that I believe that's in chapter 0. No, chapter 4. Chapter 4 has this. I just remembered. Yeah, so if you look in chapter 4, they have, I believe they have this proof of not all languages being recognizable, and then eventually giving an example of a language that's recognizable but not decidable. Other questions? Yeah.
So for this process, we're essentially, we get the input W, we ask the enumerator for the string X, and then we operate in this kind of special knowledge of that if it is an enumerator, given some time, we will get X. If it's not,
so outside of this machine, there exists an enumerator.
Okay.
And I'm working with that enumerator.
Okay.
Okay? Yeah, so this machine is only works for a single enumerator. But that I'm just converting an enumerator to a recognizer. I'm not saying that this recognizer works for all enumerators. It certainly doesn't. But because it works for that enumerator. Other questions? Yeah. No, I'm only going to accept if the enumerator printed out that string. If the enumerator printed it out, well, that means by definition, it was in the language to start with. So therefore, this machine should accept, because I want it to have the same language. Okay? Other questions? Okay, so we showed that enumerable languages are all recognizable because we can convert that way. Now we want to show the other way. So I want to convert a recognizer into an enumerator. So this one's a little bit harder, but it's not too bad. So I didn't give a name to the enumerator before, so let's make it easier on ourselves and give a name to the recognizer here. So we're going to say that let R recognize the language L. So by definition, L is recognizable, and R is the recognizer for it. So here's an important idea that will be used over and over. Is sigma star enumerable? Could I enumerate the strings in sigma star? Yeah, sir. Yeah, I actually showed an example earlier where I just print the empty string 0, 1. That's one way to enumerate the language, sigma star, but of course there are other ways. So certainly sigma star is enumerable. So what I want to do is I want to build an enumerator that, so therefore it prints out strings in this language L. And all I have with me is a recognizer. So it can only tell me if it's in the language, but not necessarily run in a finite amount of time if it's not in the language. So here's an idea that won't work. So generate one string in sigma star if R accepts, so I better give a name, W, let's say. If R accepts W, then have the enumerator print it. So certainly if the recognizer says, yeah, I accept that input, then it will be printed on the tape. So it certainly works for the strings in the language L. Is there a problem then? Exactly. I don't know in advance whether, say, the empty string is going to run forever or not on that recognizer R. I don't know that. So this strategy will not work because if I have a string that happens to have R run forever on it, then I'll never progress to the next string and then I'm stuck. And then I violated the condition that fix any string, it'll be printed in a finite amount of time. So I don't have an enumerator now. But is there a better way? So we're going to use an idea that's called run everything in parallel. Okay? So let's see. Suppose that the empty string is accepted, for example, and it runs, and it takes, let's say, 470 steps, 470 transitions. If I run it for 471 transitions, will it still be accepted? Yeah, it'll stop after 470. So maybe what we can do is try some number of strings for 1 step, then try some strings for 2 steps, then try some strings for 3 steps, try some strings for 4 steps, and keep going.
Is that kind of your computation?
It's like computation. It's like the non-deterministic thing, but in a different sense. So let's see. If we want to print some number of strings out, let's say that the string W is the, let's say, 470th, no apostrophe, string outputted by the sigma star enumerator. So the string, however the sigma star enumerator works, let's say it's the 470th string that's printed on the tape, for example. If I run W for 470 steps, could it be accepted or not? It could be accepted, it might not. What if I run it for 471? Same thing. If it takes 1,000 transitions for that string to be accepted, if I just try 470, then 471, 472, and keep going, will I eventually accept that string W? Yeah. If I just repeatedly keep progressing the computation further and further, I will accept it eventually. Another question. Is it a problem if an enumerator prints a string more than once? No. As long as I can guarantee the strings in the language will be printed in a finite amount of time. Fix a string, it'll be printed. So here's how an enumerator is going to work. Remember, an enumerator takes empty input. So it always has empty input. Well, I gotta have some counter that starts at 0, then we'll go to 1, then go to 2, then go to 3, and then I gotta run some number of strings for now I steps, or whatever the counter's name, steps. Okay, using our strategy. So initialize I equal to 1, and then so this while loop will run forever, but while I is at least 1, then we'll run some number of strings for I steps each if any are accepted by R, the recognizer. So if the recognizer accepts those strings, what should I do for the enumerator? I should put it on the tape. Then print them on the tape. With delimiters, of course. And then set I equal to I plus 1. And of course, this machine will run forever. But that's okay because enumerators can run forever. That's how enumerators work. So I hope the idea is clear that we run some number of strings, which we'll determine in a second, for I steps each. And then we'll see if any of them are accepted and print the ones that are accepted. And then we'll increase I to another, to one more, then keep going, then keep going. Yeah.
So they don't necessarily have to cross at the same time. It's just one could get to the point that it needs to, like,
yeah. So
and the other one's later.
Like if certain string is accepted at the I step, then when I go again, it'll still be accepted the next time.
Yeah, and
So,
eventually, if it's in 1, it's not there yet, it will eventually be there.
Yeah.
Okay.
Yeah. So now we have the problem of I need to start at the beginning set of strings that the enumerator will print out, and then eventually keep, that are outputted by the sigma star enumerator. Okay? I need to be able to hit in a finite amount of time each string so that I have a chance of printing it out. So what we're going to do here is a pretty smart idea. Run the first I strings in sigma star. And by the first I mean the first I strings outputted by the sigma star enumerator. However that works. So let's make sure that this idea actually works. Well, suppose that I have some string, and it's the ith string, but it requires I factorial steps or transitions in order to be accepted. It certainly won't be accepted after I steps. But increase I to I plus 1. I'll have another step to go, and is included in the first now I plus 1 strings. Then I go to I plus 2, then I plus 3, then I plus 4. Eventually, whenever I hit I factorial, I'll run it for I factorial steps, and it'll be accepted. So for all strings in the language of the recognizer, I will print them eventually. Because I will reach every string in a finite amount, each string in a finite amount of time. And at some point, if it's accepted, then I'll eventually have my I variable large enough for it to be accepted. So it works certainly for the strings in the language of the recognizer, but what about the strings not in the recognizer? Will I ever print them on the tape? No, because the only way I could print a string on the tape is if it's the recognizer accepts that string. So now the only thing we need to check and make sure of is to make sure that our enumerator fix a string will print it in a finite amount of time. So does that happen? Yeah, so fix your favorite string. If it is in the language of the recognizer, it has some number of steps to take. And so the variable I will eventually hit that number. And so therefore it'll be printed. In fact, every string that will be outputted infinitely many times. Okay? So this idea actually works. The idea of running things, so I should say this, running in parallel. So the idea of running some strings, like you're running a set of strings, each one in turn. So I'm running them for only a certain number of steps. I'm not running them necessarily to completion. So there's no problem in running here because I'm forcing the number of steps to be a fixed value or a finite value here. Okay? So we were able to convert a recognizer into a enumerator just by trying some number of strings for that many steps each, then keep going, keep going, keep going, and we were able to see that we actually print out the strings we need to print out. Yeah. Because once it's printed, then I will become I plus 1, and then it'll be printed that time. Then it'll be I plus 2 the next time, then it'll be printed there. I plus 3, still printed. I plus 4, still printed. Yeah, it'll be printed an infinite number of times, once it's printed once.
Because it's always in that first
Yeah, it's within the first I strings of sigma star. Yeah. Other questions? Okay, so this, hopefully the rest of the class will be, for today, will be a little bit less theory heavy, but more of a philosophical type discussion. Yeah, so you may think, well, these Turing machines are completely useless. We should never study them. They're not important. But I want to convince you otherwise. So I want to ask a very fundamental question. Can a Turing machine, given 2 binary integers, write their sum to the tape? Certainly a DFA or a PDA can't do this because they can't even write to a tape. And suitable presentation of the string will make it either not regular or not context free. But can a Turing machine do it? Yeah, why not? So can I use 3 tapes? Sure. Because we proved that they're equivalent to single tape. So let's have 3 tapes. And so let's have the third tape be nothing. And let's say that the first tape is 101, let's say. And the next one is 1100, let's say. And let's say I want to compute their sum onto the third tape. So we have fast computers, and there are much better ways of doing this, but is there an easy way for a Turing machine to compute the sum of, let's say, these numbers? Yeah, so, well,
Or right to left, depending on how.
so I'm going to modify the second number for a brief moment, and then I'll turn it back. What if I was given this? Then I want 101 here. What if I had a single 1 right there? Then I need to do the standard addition that we know quite well. Okay? Well, I'm going to give you another algorithm. So I'm going to turn this back into 1101. Here's an idea. Initialize the third tape to the first tape's value. Then, while the second tape is not 0, subtract 1 from the second tape, add it to the third tape. Okay? So here, an idea is make this guy 0. Then I'm going to add 1 to the third tape. So I'm going to change this to a 0 and then add a 1. And then I'll just check. Is the second tape 0? It's not here. So then I decrement the second tape. Well, how do I decrement 1100 here? Yeah, so as long as I'm seeing zeros from the right side, I turn them into 1s until I see a 1, in which case I turn it into a 0. Do I stop? Do I stop decrementing though? Yes, I stopped decrementing. So we can subtract 1 from a number, and we can also add 1 to a number. As long as I'm seeing a 1 on the right side, I change it to a 0, and then keep the carry over until I see a 0, turn it to a 1. So we can actually compute n plus 1 and n minus 1 easily. Can we compute n plus m? Yeah, it's just repeated addition by 1. Now let's start getting wild. Can we compute n times m?
Yeah.
Yeah.
Addition's just a lot of or multiplication's a lot of additions.
Yep. It's just I add n to my sum and subtract 1 from m here. So it's just repeated addition by m, let's say. Doesn't matter here.
Which each takes repeated addition by 1.
Yeah, which takes the yeah. So the idea of using previous Turing machines to compute a function used in a later one is an idea that's heavily used here. Can we compute n to the power m? Yeah, it's just repeated multiplication, which we already know how to do, by m. Well, actually by n in this case it has to be. So can we, for example, compute the exponential of a number if we take floor or ceiling appropriately? Could we take logarithms of numbers? Can we compute factorials of numbers? Is there any mathematical operation that your computer can do but a Turing machine can't? So it seems like any operation, mathematical operation, cosine, sine, tangent, whatever, that your computer can do, a Turing machine can certainly do as well. So it appears any mathematical operation a computer can do, a TM can also do.
How would the Turing machine compute the square root?
So you would have to work with the standard, let's say IEEE floating point encoding, but there's an algorithm there, and each of those components follows this sort of pattern.
The Turing machines can follow like an algorithm.
Exactly, and that'll be a huge thing in a second. But it seems like anything that a computer can do, a Turing machine can do. Yeah, can do it better. But what about the other way? So a Turing machine can certainly simulate any single operation of a computer, and then maybe multiple of those operations. Can a computer simulate a Turing machine? Yeah, certainly. We could make a, let's say, class file for a Turing machine with the transition function, and then we just run it. Oh, so it appears that computers and Turing machines are equivalent. I'm not saying at all that Turing machines are just as fast as computers, or just as efficient, or just as pretty as computers. All I'm saying is that they can do the same operations in a finite amount of time. Okay? So we should make sure that we understand the idea of being able to implement an algorithm on a Turing machine. So the idea of an algorithm, as we have known before, is that it's a finite process that always terminates and is step by step. So the spelling of the word intuitive is not intuitive. Intuitive notion of an algorithm. So it's a procedure that, so this is stuff that you should already know, that always halts and can be implemented on what we would consider a typical computer. Yeah.
So algorithms for say division,
Mhm.
where you have a repeating like 2 divided by 3.
Mhm.
That algorithm doesn't have a determination point, but we give it an arbitrary one because we want to say, limit the tolerance of the die to this.
Well, it depends on how you do it. Are you doing integer division or floating point division?
Integer, floating point. Yeah.
Well, then there's a standard mandated algorithm.
Right. We tell it.
Yeah, there is an algorithm for it. And so that follows our intuitive notion of an algorithm.
The algorithm is finite.
It's a finite process that always stops. So we'll talk about encodings in a second, maybe. But the idea of if you have a fixed encoding, let's say IEEE 32-bit, whatever,
Right.
then there's a procedure that always halts. So like anything that may take an infinite amount of time, that's not an algorithm.
Well, you're jumping from mathematical operation to algorithm.
Yeah, but pretty much every single operation used in any algorithm can either be already implemented by a Turing machine, or is just one of those mathematical operations.
Wait, so not all mathematical operations can be constructed by a finite algorithm.
But that, in terms of what a computer can do, I mean.
Okay.
Yeah, in a finite representation. Yeah, mathematical up to, yeah, you're right, to some finite precision. Because at any finite amount of time, a Turing machine can only have finite precision anyway. Yeah. But in principle, it could carry that out. If it ran forever, let's say. It could carry it out. Okay? Any other questions? All right. So the idea of a Turing machine came from this guy called Alan Turing. So we'll talk a little bit about the different models of computation that were floating around at that time. And so if you read Turing's famous 1936 paper about this, he was considering not these things called Turing machines, because that would be kind of weird calling a machine after yourself, but he was talking about these finite processes in order to generate certain numbers in terms of what are called computable numbers. And what he was able to prove is that there are certain numbers that are uncomputable in a finite process. So what he was talking about were equivalent to what we would consider a Turing machine. So these were invented by Alan Turing in 1936. But there were other mathematicians working at the same time, working on similar types of problems, but in a totally different setting. So one example that you may have seen already is something called the lambda calculus. And this was by Alonzo Church in the 1930s. And what mathematicians, including they, have found is that, in fact, these two different models used in totally different ways are in fact the same. They represent the same computable numbers. And there was actually another one that's not really that considered nowadays, but they were called rewriting systems. And then, unfortunately, I don't know a whole lot about this, but it's by a famous mathematician called Post, and you may see his name come up later in the class, maybe next week. But in fact, all three of these different models of computation are the same. And one of the results of showing that these are the same is something called the Church-Turing thesis. So the Church-Turing, so it's not exactly what it says here, but applied to the modern setting, it says that our intuitive notion of algorithm and Turing machines are equivalent. So, can I prove this result? It seems like we could, but in fact, we can't prove that. Why do you think we can't prove that? Yeah. Well, there's an infinite number of Turing machines, though, too. Because I would have to define formally what intuitive means. And until people can come up with an intuitive notion of what an algorithm is, we can't prove this result. So it may very well be that algorithms and Turing machines are not equivalent. Most people don't believe that. Most people believe the Church-Turing thesis because everything that, the most fundamental part of an algorithm is simple addition, and Turing machines can do that. And everything else just builds upon that idea of addition. So it seems very true that the Church-Turing thesis is true, but I can't prove that. Okay? Or anyone can't prove that. Okay, so this idea of the Church-Turing thesis is really important because you can't just say Turing machines are not important because, in fact, they rely on our very notion of what algorithms are. If I can make a Turing machine decider for some problem, then I know that my computer can also solve it. If I can prove that for some problem that it is not decidable by any Turing machine, then I can't do it on any computer, no matter how fast, how fancy, anything. Okay? Any questions about that? So we have like 15 minutes. I think we can start the next bit. So this is when we start getting into a more high-level approach to the class. We're not going to look at details of Turing machines or any machine for that matter. We're going to be looking at how to solve a particular problem and show that either it's decidable or show it's recognizable or show it's neither or one or the other. But to do that, we need to be able to present the inputs that we care about, say like a graph or, let's see, maybe HTML syntax, for example, or any type of input that you want to give to a Turing machine. We need to have some kind of way of presenting it to a Turing machine. Or a DFA, if I want to present a DFA to a Turing machine, how am I going to do that? Okay, so that's the idea of an encoding. Okay, so an encoding, I'm not going to give a formal definition because it's really an informal type thing. It's a way of specifying to the Turing machine a particular input. And so the only property that we really want out of an encoding is that I give it some format of this, let's say a graph maybe, and then in a finite amount of time, the Turing machine can extract all the information that it needs out of that encoding. So like, for example, if I present an adjacency matrix to a Turing machine, like row 1, delimiter, row 2, delimiter, whatever, that is an encoding of a graph. Or maybe I could have a vertex, comma, vertex with delimiters on either side. That's another encoding. So because the encoding can be entirely different depending on the object that we're working with, we're not going to be necessarily worried about how it's presented to the Turing machine, but we got to make sure that however we present it, it can be recovered by the Turing machine in a finite amount of time. Yeah.
So you're basically talking about an abstraction.
Yes, yes, absolutely an abstraction. Okay. So I want to talk about one simple problem, and we want to show that this problem is decidable. So I have a Turing machine that will always halt given a particular input of the correct form using the encoding, and tell us either accept or reject in a finite amount of time. So one of the really first problems that we saw in the class is given a DFA, we trace through a string and figured out whether it accepted or not. So a problem of this nature is called a DFA. And I'm just going to write it down, and then I'll explain the notation. So I'll talk about these angle bracket things in a second, but it's composed of all pairs M and W, where M is a DFA and W is accepted by the machine M. And so this pair belongs to the language a DFA if it's of the form machine with a string and the machine accepts that string. So you may be wondering what this is. So this is an encoding. So a DFA by itself is not a string. So I can't present it to the Turing machine. But what I can do is put it into some encoding in some way. Maybe I write out the states first, then I write the input alphabet, then the transition function, then the start state, then the final states as a string. For all the Java programmers out there, this is just like a toString, or a repr if you're a Python programmer. So like a suitable encoding of a DFA may look like this. So we would have, let's say, delimiter Q0, Q1, Q2, Q3, Qm, let's say. Then, so these are the states. So whenever I put angle brackets around something, that means encoding of the thing. So if I want the encoding of just M by itself, then I have, let's just say for a particular example, I have states followed by symbols, let's say P1, P2, up to PK are the symbols in the input alphabet. Then the transition function, which what we could do is say the state name that we're in, symbol, then the next state as a triplet. And then separate the triplets by another delimiter. So let's say smiley face, Q1, A, let's say Q3, smiley face. And then I carry on through all the other transitions. Then let's say Q0 is the start state. So this wraps around. And then final states, let's say Q2, Q3, Q7 throughout. So I'm not saying this is the encoding because we can, as long as we set up a suitable encoding of the DFA, as long as the machine can extract the information it needs out of this DFA in a finite amount of time, I don't care what the encoding is, as long as it's some encoding. This is just one encoding, but it could be any encoding. Yeah.
Are the angle brackets kind of a standard way?
Yes. Yeah. So we'll be using angle brackets through the rest of the class. Yeah. So angle brackets M, comma W just means some representation of a DFA with the input somewhere in there. It may be right after, it may be right before, it may be mixed. I don't know. It's some encoding. Okay? And I don't care how it's presented as long as the machine can find out the required information from M and W. Okay. So I want to claim that a DFA is decidable. So I want to outline a high-level description of a Turing machine such that given this pair, M and W, it can decide for me whether or not the machine M accepts W in a finite amount of time. Okay? So I want to make a decider, let's just call it D. So D here is the name of the decider that I'm going to make. Well, it's going to be presented some input of maybe of the form MW as an encoding, maybe not. So let's say it has on input MW, where M is a DFA and W is a string. So this little check at the beginning where it says where M is a DFA, W is a string, that's just making sure that, it's just making sure that it's formatted correctly. It's not given garbage input. So it can actually extract the information about the DFA in the string. So now, once the machine has verified it is a DFA and it is a input string, how could I check whether that DFA accepts that whether that DFA accepts that string or not? Don't think too hard. Just run the machine on the DFA. So run M on W. Let's just check. Does this step take a finite amount of time, or could it run forever? A finite amount of time, because every single time we chew through one character of the input W, and then eventually it'll run out of input. Well, how will I check once it ran out of input whether M accepted W or not? If it's in one of the final states. So if M ended in a final state, what should I say, accept or reject? Accept. Good. Otherwise, it did not end in a final state, and so what should I say? Reject. Does this second step take a finite amount of time or not? Yeah, certainly I can just check what the state is that I'm keeping track of, if it's a final state or not. And so therefore, this language is decidable because this machine D halts on all inputs. And it says the correct answer because it only accepts if the machine M accepts the input W. Okay? Any questions like that, about that?
So it's like with these proofs, we're not even really doing anything. We're just saying that something.
No, we are doing something.
It can be done. So.
Yeah.
So it's like so.
I know there's an algorithm that has a DFA run on an input, so I just use it. And yeah, go ahead.
Oh, I was just going to ask, like, to make this complete, we have to summarize that it is by definition decidable, or is that?
You should say you should say step 1 runs in a finite amount of time because you consume one character every transition. The second step runs in a finite amount of time because you just check what state you were in. And it's clearly correct because you only accept when M accepts W. Okay? And so this high-level approach is the way we're going to go through the rest of the class. Not just today, but through the rest of the semester. Any other questions?
How are tests going to look like with this?
So it'll be presented something like this, and it'll say, show that this is decidable or recognizable or whatever. Yeah. Not yet. So you want me to give you an example but not prove it? Sure. So here's a language that is recognizable, but so I will probably prove this either Monday or Wednesday, but not decidable. And it is, I can give a lot of examples, but the prototypical example is ATM. So the only difference between ADFA and ATM is that M is a Turing machine. That's the only difference. So this is at the end of chapter 4. You can actually, if you want to skip ahead, you can see the proof of why that's not decidable. And the strategy of just run the machine on the input certainly can take an infinite amount of time. But that does not prove that there is no algorithm for ATM. If we want to prove that ATM is not decidable, then we'll need some other techniques. Okay? Let's do one more decidable one, and then I'll let you go. So instead of ADFA, I want to ask the question about NFAs this time. Exactly the same question, but for NFAs. I want to show that this is decidable. So can I make a decider that always halts for this problem? Exactly. Convert it to a DFA. Does that run in a finite amount of time? Yes. So here's the algorithm. So on input MW, I'm not going to say where M's an NFA. It should be pretty clear what it is. Convert M into an equivalent DFA, and I'm going to call that DFA D. Well then, since it's an equivalent DFA, what have I just reduced to this problem to? A previous problem. So how about I run a DFA on it? So I'm going to write something down, and it's not going to be right. So I'm going to write down run a DFA on, well, it's got to be given a machine and an input. So D and W are my inputs. But this is not correct. It's what I want to happen, but it's syntactically not correct. What is a DFA? It's a, what structure is it?
It has to be in a certain form.
Is a DFA a machine, or is it a language, or what?
Oh, it's
But it should needs to be an input string format or whatever.
I'm running a machine on a string. But what is a DFA?
it's an encoding.
It's a set of strings. What is a set of strings? A language, by definition. Can I run a language on a string? No. What can I run on strings? Strings. Machines, yeah. So instead of saying run a DFA on it, I run the decider for a DFA on that string. I can't run a language on a string. Okay? So I'm going to move this out of the...
And one more thing, a decider is an input string that has a example, right?
A decider is a Turing machine. A language is decidable. But a Turing machine may or may not be a decider. Okay? Nouns versus adjectives here. Yep. So run the decider for... yeah, this is something I see students do a lot by saying, run this ADFA on whatever, or run a NFA on whatever. But that's actually not quite correct because it's missing the notion of what a language actually is and running a machine on a string. But I know the decider for ADFA runs in a finite amount of time, so step 2 takes a finite amount of time. And then I just need to say output what the decider says. So correctness is good here because the DFA has the same language, but is it a decider? Step 1 runs in a finite amount of time, as we said. I assume by earlier discussion that step 2 runs in a finite amount of time, and step 3 certainly does too. Any questions about this? All right, I'll see you next week.